Hello all, and welcome to today's lesson on transformations. Our first kind of transformation that we're going to look into is called a translation. So we're going to learn what is a translation and how can you carry them out, or if you see a translation, how can you describe it in vector form. So in general, a transformation is a change in a shape something, 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 and something. So let's try to think what they might be. In general, a transformation is a change in the shapes. So something in terms of its size. So it's a change in a shape size. Try to think what that would be. That's right, yeah, position. So a change in a shape size, position. What would this one be? Shape. And try to think of the way it's kind of situated in space, starting with OR. Orientation. So transformation is a change in a shape size, position, shape, and orientation. There are different types of transformations, and our syllabus covers these kinds of transformations. So types of transformations we'll cover in this unit include the first one. What is today's lesson about? That's right, it's translations. Translations. Try to think, what's another kind of transformation, like a movement in space that starts with RO? That's right, it would be rotations. Hopefully you're writing better than I am. In terms of mirror images, try to think mirror images, they generate things called reflections. So that's another one we'll learn about later. So translations, like movements up and down, up and across, down and across, that kind of thing. Reflections, rotations. In terms of things getting bigger and smaller, how can we describe that? That's right, it would be enlargements. Oops. Just 1 second. Let's write better. Enlargements. Enlargements. Really doesn't want to do that, does it? Just put the camera again. Enlargements and, so getting bigger and getting smaller, reductions. So translations, rotations, reflections, getting bigger and smaller, enlargements and reductions. Try to think, what do you tend to do when you warm up to do sport? You do a thing called stretching. So that's in the last kind we're going to look about stretches. So we're going to learn them in this order. Translations is today. The next lesson is rotations, reflections, enlargements and reductions is a single lesson, and stretches. Stretches is when it kind of stretches in one direction only. So enlargements, they kind of stretch out in all directions, or they shrink in all directions. The stretches, they kind of stretch in one direction only. So label each diagram below with the type of transformation it demonstrates. So it's either going to be a translation, transformation it demonstrates. So it's either going to be a translation, a rotation, a reflection, enlargement or reduction, or a stretch. So let's have a look at these pictures below and see what they kind of seem to match up with. So notice that the object is the original diagram, and the image is what you see after the transformation has taken place. So see the object, in this case, just label it in red, is our object. So I might put it in red just to point out what it was. The object is the original diagram, and the image is what you see after the translation has taken place. So the image, if you want, we can label that in purple. So the image is like the result. The object is kind of what you had originally, and the image is the result of the transformation. So we've got a mirror line here. What kind of transformation do you think this would be? Have a guess? That's right, it's a reflection. So later on in other lessons we're going to be learning about reflection. Just a reflection. You can put reflections, but that's okay. But it's a single reflection. So the one in the top right, so again I'm going to just practice, okay, the object, circle that in red, just so you get used to the idea. The The object is the original, the image is the result. That's good terminology in terms of the way questions are worded. They require you to realise the object is the original diagram, the image is the result you see after the transformation. So what kind of transformation could this be? Is it a reflection? Is it a rotation? It doesn't seem to be. It seems to be more that image has moved across by 4 and down by 3. That is actually called a translation. So that's what today's lesson is about, translations. Moving up and down or left and right, and the shape and size of the image doesn't change at all. So that's what we call a translation, because we can see it moved across by 4 and down by 3. Let's look at this middle one here. See, we've got our object. Our object, let's label that in red. So there's two different transformations going on here. There's one where the image slightly changed out here. Another one where the image is down here. So these are two different transformations, but they're both the same kind. So try to think this, and going from the middle one in red to the one in the right in purple, did it get bigger? Slightly did. Did it get taller? No, it didn't get taller. Did it just stretch in one direction only? And yes, it stretched to the right. So this little point here stretched and became that point there. Whereas these original points here didn't move at all. So that's what we call a stretch, where it moves in one direction only. It's not an entire enlargement or a reduction, because it didn't get taller. It just stretched horizontally. So a stretch is when it kind of increases or decreases. Say in this case, it became a bit smaller. This one stretched inwards. These 2 points stayed the same. So the stretch is when it stretches, gets bigger or smaller in one direction only though. That's what we call a stretch. Let's see what other kind of transformations do we have here. So we have on the left, we have our object. And again, we've got a few different versions of images. So after one transformation, it was here. So what kind of transformation would we call that? It's not an enlargement or a reduction, it's still the same size. Not necessarily a reflection, because the purple image is not a mirror image of the red object image. So what would it be? At an angle kind of 120 degrees gives you a clue. It's a rotation. So that kind of transformation is a rotation. Also, there's a second rotation where it went to 40 degrees. It also became here. So it's just more like this whole diagram shows two different transformations, two like rotations. That's why you have two different images. Okay, so back to this one, the middle one, we've got our object. Again, let's label that with red, so you get used to the idea. Object is the original, and the image is the result you have after the transformation has taken place. What kind of transformation do you think this would be? Is it a reflection? No, because they're not mirror images of each other. Is it a rotation? No, because the 3 points, the 3 vertices, are still kind of oriented in the same kind of way. Is it a stretch? I would say not a stretch, because all points kind of moved in. Like it's reduced, but it's reduced vertically and horizontally. So in all directions, it's been a reduction. That's what we call a reduction. It's basically shrunk. So it's the same shape, same vague orientation, it's just shrunk in size. So all 3 points have moved inwards by the same amount, by the same length. So what's this last one here? So we've got our object here, that's our original diagram. And we've got our image, which is the resultant diagram after the transformation has taken place. Right there. Okay, so you probably guessed already. So you've probably seen all 3 points have been moved outwards by the same amount. That's what we call an enlargement. That gives you an overview of what we're learning about in this whole unit. So enlargements and reductions and so on. Let's go on to translations. So what is a translation? That's what we're focusing on today. A translation is when an object moves from one place to another. Every something on the object moves in the same something and the same something. So a little clue is every What are these little things being called? They are called coordinates. So what else could you call them? Points. So every point on the object, so every point, every little coordinate on the object moves the same. What's this thing here? That thing there. The same, starting with D, distance, and the same direction. So every single point, this top right point here, has moved the same distance and the same direction to become down there. So this point here moved the same distance, the same direction as the other point which moved there. This point here moved the same distance and direction to become there. This point here moved the same distance and direction to become there. That's what we call a translation. So try to think, how could we calculate the distance moved by each point? So the distance moved by each point, I'll just kind of point out what I mean. Like this length here, the distance moved by each point in red. So imagine if that was x. We could kind of set it up like this. That's our x. Dot, dot, dot. There's this is 4, and this is 3. It's kind of negative 3, but it's also 3, moving down by 3. And that's a little right angle there. Something that we've learnt about in a previous unit that we can use to calculate this distance x, because we have a right angled triangle, we can use Pythagoras' theorem. We can use Pythagoras' theorem. Oh my goodness. Pythagoras' theorem. So we could go x equals square root of 4 squared plus 3 squared, or 4 squared plus negative 3 squared, same thing, equals, if you want to do it without calculator, 16 plus 9 equals square root of 25 equals 5 units. So that's the distance moved by each point. So that red line represents 5 units. So we can actually use, if we know the distance has gone across and down, we can use Pythagoras' theorem to therefore calculate the distance. Down a bit. So when we describe the translation, sometimes you're asked to look at a picture and describe the translation. Again, just reminding you, here's our object, here's our original object, and here's the image. You just get used to those terms. I'm putting them out like this. So when we describe the translation, we need to mention how many units the object moves in something direction, in the x direction, and something in the y direction. So starting with h, when we move in the x direction, which direction are we moving? That's right, we're moving horizontally. So how many units the object moves horizontally in the x direction and vertically in the y direction? So in the above diagram, the object moved how many units in the x direction? It moved positive 4 units in the x direction because it moved to the right, and it moved negative 3 units in the vertical direction because it moved down by 3 units. But to do this, we use a thing called vector notation. So you learn formally about vectors later on in this course, like in year 11, but vector notation is easy enough for you to be introduced to now. So let me kind of show it to you below. We're not learning about everything to do with vectors, just about basic vector notation. So let's say pxy means the original point, or, like we do like to say coordinate, but I'll probably be saying point. So by points or coordinates, same thing. So pxy is the original point of the red diagram, which is located at the coordinate position xy. So basically, it's a point that was on the original diagram. Now this is the vector notation. Vector notation is generally in this kind of style. Basically, you have bracket, and the H stands for the horizontal movement, like how many units horizontally. The K stands for how many units vertically. So this vector notation means the point P, the original point P, which if you're not sure of, is that thing there, is to be moved H units horizontally, because H represents the horizontal movement, the x direction and k units vertically in the y direction. For instance, in the above diagram, the translation vector would be, so you'd have a bracket. So let's say we went across by 4 and we went down by 3. So the way we would write that, we have our little bracket set up, our tall brackets, and our h is our horizontal movement. It moved 4 units to the right and 3 units down. So it moved 4 units to the right and 3 units down. So let's describe that. 4 units to the right, so in the positive x direction, and 3 units down, so in the negative y direction. So that's what that means. So this whole shape is the exact same shape and orientation, it just moved 4 units to the right and 3 units down. It didn't flip around, it didn't rotate at all. That's all that happened. Whereas P dash, X dash, Y dash is the point which results due to the original point P going through the transformation. So let's just show an example of that here. So if this is, let's say if this one was P, and this one here would be P dash. You can see they correspond to each other. These 2 points correspond to one another. And if this one here was A, then this one here would be A dash. So the original ones, the ones that don't have the dash, appear on the object. The points, the coordinates that do have the dash on them, the apostrophe, they appear on the image. Okay, so under a translation, the size, shape, and shape of an object does not change. Only the position of the object changes. So that's what. Let's do some examples. So A, translate the quadrilateral ABCD, which is in the diagram to the right, bottom right, 2 units right and 4 units up. So let's try doing that. Interesting. So you might want to kind of look at the points. Here's the object. Use its points. So each point, as it says, each point 2 units right and 4 units up. Let's start with A. So we need to go 2 units right and 4 units up. So I've gone across by 2 and I've gone 1, 2, 3, 4 units up. There's my A dash. And B, we've got to go 2 units to the right and 4 units up. So count 4 units up. It is. C, we've got to go 2 units to the right and 4 units up. 1, 2, 3, 4. And D, 2 units to the right and then go 4 units up. And hopefully you've got it there. Notice that it looks quite similar. So now let's just connect up those points, and the diagram should look exactly, under translation, the diagram should look exactly the same as it did before. It's just moved sideways and upwards. It could just only move upwards, or it could just only move sideways, in which case one of the vectors would be 0. But in this case it happened to move horizontally and vertically. So B, describe this translation vector using, use a translation vector to describe this translation. Okay, so set up your big brackets, tall brackets, and horizontally is what goes first. Horizontally and then vertically. So don't get those two mixed up. Some people do vertically first and then horizontally. That's what you can get mixed up. So it moved 2 units right, so that's in the positive direction, positive x direction. 4 units up is the positive y direction. So there's no negative there because it didn't move down or it didn't move left. Okay, cool. And state the vertex coordinates of the image quadrilateral. So what on earth are they asking there for the vertex coordinates of the image quadrilateral? So let's see, this one here, that would be A dash. Let's see, A dash, because it's in the image, it's not in the original one, object. So what are its coordinates basically? So it's -1 in the x and 3. And -1, 3. Easy, done. Now let's do what B dash would be. B dash would be this one here. So B dash here would be 1 and 1. C dash. C dash would be this one here. That is 1 and -1. C dash, 1 and -1. Last one would be D dash. D dash is this one here, and it is -1 and -1. So that's what they're asking. State the vertex coordinates of the image quadrilateral. So the vertex meaning the corners, so its coordinates. If it helps, you can always label it. You can put that one A dash, B dash, C dash, D dash. You have to, but I didn't ask you to do that. But it can be very helpful to do that. Find the distance moved by each point. So the distance, remember, how do we calculate the distance according to the previous page? We use Pythagoras' theorem. Pythagoras' theorem. I've done it again. Pythagoras' theorem. So when you think it's moved, according to our translation vector in green, each point has moved 2 units across and 4 units down. So 4 units up, sorry. So each one will have moved 2 units across and 4 units up. And they want us to calculate what the distance is that each point has moved, x. So let's work out that is. So x will be square root of 2 squared plus 4 squared, which equals square root of 4 plus 16 equals square root of 20. Now let's practice using surds. How would we simplify this surd? So what's the biggest square that goes into 20? It helps to do this. 4 by 5 equals 2 root 5 units. So good to practice using our surds. And we get nice exact answers. Unless it asks for the answer to 3/16, in which case we have to use that calculator. So that was an example, a very classic example you might be asked to do in an exam or in a textbook exercise. So we can relate translations to equations of straight lines. So equations of straight lines, remember back to coordinate geometry, y equals mx plus c. What does the m stand for? It is the gradient. What does the c stand for? It is the y-intercept. So equations of straight lines. So we can relate translations to equations of straight lines and use our skills in coordinate geometry, because you're experts in them by now, to find the equation of the image. Remember, the image is the result that happens after the transformation has occurred. So on a set of axes, let's first of all just practice our coordinate geometry. So there's no transformations in this first part. Just on a set of axes, draw the line y equals -3/2x plus 5. So different ways you can do it. You can find the x and y intercept first. That's okay. Remember to find the x-intercept, y is 0. To find the y-intercept, x is 0. Feel free to do that. I'm going to plot the y-intercept. Intercept is a +5. I'm going to plot the y-intercept first, and I'm going to use the gradient to plot some more points. So rise equals, I'm going to say rise is -3, the run is +2. So I need to go to plot from 5, to plot another point, I need to go down 3 and across 2. So go down 3 and across 2. Let's do some more. Let's go down 3 and across 2. Down 3 and across 2. Click on that, right? And then I just use our little line, use a ruler basically, to draw a nice line through there. So because it's our original object, that's our object line, I'm going to do it in red. And I'm going to try to make that look a bit better. Okay, there we go. A little bit better. And remember back to coordinate geometry, what should we, there you go, let's do that. So coordinate geometry, what do we also need to do to make it all nicely presented? We need to label our equation. So let's label our equation. Maybe I'll put down here. Y equals, space, -3/2x plus 5. Okay, so we've done the first part, tick. Then, find the equation of the image when the line is translated through, this is the translation vector, -1, -2. So we need to go, each point needs to go down 1. Oops, whoops, what did I do wrong there? Should be horizontal first. So each one needs to go left by 1. So left by 1 and down by 2. So because it's -2, that's why vertically it goes down, and it's -1, so horizontally it goes to the left. So left by 1 and down by 2. So feel free to do that to each point. So here's your first point. So I'm going to do the image in purple. So we need to go, actually I'll do the points in blue and I'll draw the line in purple. So I need to go left by 1 and down by 2. So from the y-intercept at 5, let's go left by 1 and down by 2. There we go. Right, I hope so. Now the next green point here along, we're going to go left by 1 and down by 2. Be really careful with the way you draw them. And the next point along, go left by 1, down by 2. Next point across, go left by 1, down by 2. And now I'm going to use my ruler to come up with a nice line, which I'm going to try to do in purple. Here, it's a rough drawing of it. Make it look better. Cool. So so basically I've drawn the line. So the first thing is you probably want to draw the line. Now we need to find the equation of the line. So the equation of the line is y equals mx plus c. So what's our y-intercept this time? Let's see. Our y-intercept, it's kind of a little bit harder to see, isn't it? But you could always use a point to find the y-intercept. What do you notice about the gradient? That might help first. The gradient stays the same. So the gradient does not change under a translation. So that's helpful. So we can say the gradient is the same as before. It's -3/2. So let's write that. Y equals sine -3/2 x plus c. And then maybe use another point. So what's another point that we've got? So let's see, you can use any point you want. I might use a nice easy one. We're going to use sub in a nice point to find what c is. So I'm going to use this one here. What's the coordinates of that point? So that point is, we'll just put here, 1, 0. And we're going to sub that in for x and y. So this is good practice with coordinate geometry again. So our y is 0. 0 equals -3/2. And it's all because we can't easily see the x-intercept. It could be 1.5, but maybe it's 1.3 or maybe it's 1.55. Let's just double check by being really careful and actually subbing in a point to get the correct value. So our x is 1 plus c. And I'm going to solve for that. So we can go 0 equals -3/2 times 1 is just easy, -3/2 plus c. We're almost there. So our c must be equal to +3/2 or 1.5. So let's write our final equation. Our final equation is what we just originally had. So it's y equals -3/2x, same gradient, plus 3/2. And have a look at your diagram. Does it make sense? Let's see. The y-intercept is at about 1.5. So it's always good to double check. You might have a really weird answer. You might have come up with -1.5 by mistake. And then by looking at the image line, the purple line, you would realize something was wrong. So that's how you can use a translation and find the equation. Notice the language they used. Find the equation of the image when the line is translated through this. So good to draw the original line, do the translation, and then you can kind of use your coordinate geometry. And then you've got lots of different ways to back up your answer. You've got the graph to look at it, you've got the algebra to prove it as well. Another example. Translate triangle M by 2, 3. So what do we mean by triangle M? It's down there. So we've got to make it go through this transformation. So move it horizontally first and then vertically. So it needs to go right by 2. If it helps, right and up by 3. So in case that helps you write that out, it needs to go to the right by 2 because horizontally it's +2, and up by 3 because vertically it's +3. Label your new triangle N. So let's do that first. So here's our object. These are the points on the object. It can be good to do the little points first. Now let's make the image. Let's remind ourselves what we have to do. We need to go right by 2 and up by 3. Right by 2, up by 3. So from the top one here, I'm going to go right by 2, up by 3. Here it is. Then the one to the bottom right, I'm going to go right by 2, up by 3. Here it is. Then the one to the bottom left, right by 2, up by 3. Here it is. There we go, we've done. And what it says, translate, label your new triangle N. So now we're going to do that. Connect them all up. Actually do the triangle. Use your ruler. Do freehand horrible stuff like I am. That's awful. See, the first one was labelled M. Let's label the new one. Nice purple. M. Lovely. So the object is down in red, green in this case, and the image I've done in purple. Yeah, so that one, yay, done. Now translate triangle N. So not triangle M, but triangle N, the new one that you did. And I want you to translate it this way. See that translation vector? Label your new triangle P. So each point on N, each blue point, we're going to have to go left by 9 and down by 3. So again, if that really helps, write it out, because it means you're going to think about it a bit more and hopefully do the correct translation. So remember, horizontally first and then vertically. So you're going to go left by 9 and down by 3. Left by 9, down by 3. That's all from these blue ones. Left by 9, down by 3. I might do this in a nice mauve. Make a nice colour. There's a nice mauve. Okay. So left by 9, what was it again? Left by 9, down by 3. Yep. Okay, so left by 9, this is painful. So the top one, go 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, it's here. So you can left by 9 and across by 3. Double check it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, down by 3. I forgot to do that. That. Down by 3. Oh, and it's not pink anymore. I think. There you go. Left by 9. Left by 9. Down by 3. First one done. Now the bottom left one I'm going to do next. Let's go left by 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then go down by 3. 1, 2, 3. Lovely. Left by 9, down by 3. And make sure we're doing this all relative to this purple one here, from N. We're using N. So now this one here, we're going to go left by 9, bottom right. 1, 2, 3, 4, 5, 6, 7, 8, 9. And down by 3. 1, 2, 3. Oh, that's good. And now let's draw a triangle. Use a ruler, connect up. P. Have I done what they asked me to do? And does it look about the same? It should be about the same shape and size. It's just in a different spot. P. It does make sense because N went up by 3 and this one's gone down by 3. So it should be vertically in the same position as M, but it's just moved to the left. So what single column vector would move M onto P? So a single column vector, they just kind of want you to, they mean that. They mean translation vector. So what is a translation vector that would move M onto P? Let's look at the picture. So drawing the picture helps a lot. So So M, so let's see, this little point, it didn't move up at all, but it moved across, moved to the left. 1, 2, 3, 4, 5, 6, 7. 7. And that little point didn't move vertically, no, it didn't at all. So it's just 0. And it makes sense, doesn't it? Because going from M to N, you kind of went up 3 and across 2. Then going from N to P, you went down 3, so it cancelled out the vertical movement, and across 9. So by going right by 2 and left by 9, overall it's a movement of 7 to the left. So that makes sense. So same thing with this, you can check with this one. It's 1, 2, 3, 4, 5, 6, 7. Check with the other one if you want to. So move 7 units to the left. So again, it's pretty obvious stuff. It's just understanding what on earth is the person asking me. What's this funny language? And thank you, and that's the end of this lesson.